Hey guys, this is academic chemistry. We are in chapter 6. We are talking about the periodic table. We've gone through all the history, but today we're going to talk about periodic trends. So, what makes the periodic table really handy to use besides just identifying if it's a metal, metalloid, or non-metal, and the different valence electrons and stuff? But what about the trends? How do they interact with one another? There's three trends we're going to go over. We're going to go over atomic radius, we're going to go over electronegativity, and then we're going to finish up with ionization energy. Okay, so if we're going to talk about atomic trends, we also kind of have to review what the atom looks like. So I put a picture up here to just kind of refresh your memory about an atom. Plus, this picture is very exciting. So look at all those colors. So let's think about what's going on here with our subatomic particles. We've got protons, neutrons, and electrons. So in the center here, we've got those protons and neutrons. So protons have a positive charge, neutrons have no charge. Swarming around on the outside are the electrons, which have negative charges. Now, this picture doesn't fully give it justice. It doesn't show you the energy levels. It doesn't show you the orbital shapes. Remember S, P, D, or F. It just kind of shows them in paths. And electrons don't stay in the same path too, which brings me to my first point that we have to keep in mind. Electrons make blurry paths within their orbits. So an electron isn't constantly going the same motion. It might go over here and then there and wherever within that shape, within the S, P, D, or F shape, whatever it happens to be assigned. So you can't exactly see the edge of an atom. The next thing you need to know for trends is that the nucleus, since it has those positive protons right in the center, so this whole center part is all positive, and the electrons are swarming on the outside and they're negative, the electrons are actually pulled in towards the atom, and that keeps the atom together, is that opposites attract principle. So all the electrons are being sucked into the center of the atom. And the other key thing to remember with all of these is electrons repel each other. Electrons repel other electrons because they have the same charges. And since opposite charges attract, same charges repel. The first trend we're going to talk about is the atomic radius of the atom. And I'm going to bring up again, we can't directly measure the width of an atom because the edges are fuzzy. So I'm re-emphasizing the edges of an atom are fuzzy. If I look at these two hydrogen atoms, notice you can't exactly tell where hydrogen ends, right? So I can't just say, if I want to know how big the atom is, it's from here to here, from the outside parts. Obviously that's way big because you can't even see atoms. But you can, even looking under the electron microscope, you can't see really the edges. But what you can see is you can see the nuclei. Now I drew little circles here to represent the nuclei, but keep in mind the nuclei are incredibly dense and they're super compact. We can really think about, for what this class, the purposes of this class, you can think of all atoms of having an equal size nuclei. They're just so incredibly small. That's not true. They are very different in sizes if you get to quantum mechanics and all that. But for the purposes of this class and getting familiar with your elements, just think of the nuclei as these little teeny tiny specks within each atom. So since the nuclei are so clear, the atomic radius is found by comparing those two atoms of the same element next to each other and tracing a line between the nuclei, because we can clearly see there's the nucleus and bloop, there's the line between them. So half of this line is going to be the radius of one atom. And then that can evaluate the radius is half of the diameter, or the full width of an atom. So we can just compare all of the radii of an atom. Let's look at the atomic radius trend across the periodic table. So we're going to first start with periods. So that's right to left, left to right. And if you take this period where we start with potassium and end with krypton, you'll notice that as you go to the left, your atoms actually are bigger. So your radius increases towards the left on your periodic table. Why is that? Because there's less nuclear pull. Remember, those are the number of protons in the nucleus. And you have the same volume of electrons. And what I mean by that is the maximum energy level they can get, the biggest they possibly could go out to because of how much energy they have. Okay, so we're all in the same period, so we have the same maximum energy levels of the atom. If you have the same maximum value of where electrons could go, but you have less pull inwards, then you're going to have a bigger atom. So the less nuclear pull you have, which is towards the left-hand side, right, lower atomic numbers, then you're not going to pull the electrons in as much. So let's see, this is an atom of potassium. Notice I have a plus 19 in the center. I've got 19 protons in the center. I've also got 19 electrons floating around here. But basically, each one of those electrons feels the full nuclear pull of 19 inward pulls. Versus krypton. Krypton is in the same period, so it still only goes to the same maximum energy level. But those electrons are feeling that positive 36 pull inwards. That's almost twice as much of a positive pull inward on each electron that it feels. So what ends up happening is in krypton, it pulls it in. Do you see how all the electrons got sucked in by that positive nucleus that was so much stronger? And since it was a stronger nucleus, all the electrons got squeezed in. All right, so what else happens? Here is up and down a group. So you'll notice that the radius of an atom increases as you go down the periodic table. Why is that? Well, as you look down the groups, you'll notice atoms have more energy levels filled on the bottom, and that's going to make the atom bigger. And what I mean by that is how many shells. So, hydrogen only has electrons to the first shell. Lithium has electrons in the first and the second, sodium, third, potassium, fourth, rubidium, fifth. And as you go on, you get a bigger atom. Now, one way I like to think about this, and just to keep things track in my head, for atomic radius, the biggest atom there is francium. So right under cesium here is francium. It's not really there because you don't see it very often. It's a very rare element to run into. But if I ever forget which one's the biggest, I think about how big the Eiffel Tower is. That's a pretty darn big statue or monument. So the biggest one is francium, named in honor of France. The smallest sized atom is helium. So think of those helium balloons and those teeny tiny little helium atoms, and think about how small they are compared to the big Eiffel Tower in France. And that's just a little fun way for me to remember it. Now, some of the problems you're going to run into in this is putting things in the proper order. Now, whenever you're putting things in order and according to atomic trends, this is what I want you to do. I want you to look and see where they are on the periodic table. So this question says, put the following atoms in order of increasing atomic size. So I've got sulfur, fluorine, and antimony. So where is sulfur on the periodic table? Okay, it's right there. Where's chlorine? There. And antimony? There. I remembered that my helium balloon is the smallest. So helium atoms are the smallest atoms. And francium down here are the largest. So if I'm putting them in increasing order, I'm going to start up in the top right corner and track everything to the bottom left. So my smallest of these three elements is chlorine, followed by sulfur, and then antimony. Let's do another one. Oxygen, cesium, and bromine. So let's find them. So where's oxygen on your periodic table? It's right above sulfur. Cesium is in the far left side, and bromine is right under chlorine. Now this one's a little tricky because you're like, I don't know, bromine's down, but it is to the right. You got to think about energy levels when they're that close. So if I'm going to put these in order, the smallest one is going to be that one that's the closest to helium, which is oxygen. Bromine is then the next biggest, and cesium, since that's right next to francium, that's a pretty darn big atom. For this list here, cesium would be the largest. The next trend we're going to look at is electronegativity. So the first thing we need to do is define that. Electronegativity is the ability of an atom to attract electrons. So atoms always interact with each other's electrons to make bonds. And if you're going to make a bond, you need to be able to pull an electron from another atom. These values range between 0 and 4, and 4 is the strongest of the atoms, or the most able to steal electrons. So when you think about electronegativity, I want you to think about who's the biggest bullies on the periodic table. Who's wanting to just like take electrons from other atoms, just give me your electrons, I don't even care. All right, so if we have sodium and chlorine, for example, if there's an electron between these two, since sodium's electron negativity value is 0.9, it's not even 1, and chlorine is 3.0, Chlorine is 3 times as strong as sodium is. So chlorine, I mean, it's more than that, really. It's more than 3 times as strong. So chlorine obviously is the stronger of the two. It is more electronegative, and if you're more electronegative, you're able to pull electrons from other atoms. So this electron is going to be attracted more to chlorine and than it is to sodium. This is going to determine what type of bond happens. And we're going to go through this in Unit 3, but I just wanted you to be aware. We're going to come back to electronegativity. This is definitely the most important, in my opinion, periodic trend to learn because it's going to really dictate the next student and how well you comprehend that. Noble gases have no, or sometimes they have very, very, very small, but generally have no electronegativity values because they're electrically stable. Remember when you did the electron configuration of noble gases, we talked about how the noble gases don't really make bonds. So they're not trying to pull electrons from another atom because they're not trying to pull an atom over. They like to hang out on their own. Plus they have that full valence shell. The goal is to always have 8 valence electrons, and noble gases already have that. They have their complete octet, so they don't want electrons from anyone else. They're like, I'm too busy being awesome and a noble gas to take one of your electrons. That's what they say to other atoms. Just making sure you guys know atoms don't actually talk. I give them personalities all the time, I know. Let's talk about the periodic trends of electronegativity. So first, we have to keep in mind that we're really going to ignore the noble gases as far as electronegativity. If you're putting anything in order, the smallest electronegativity value is always going to be a noble gas. What happens on the periods? So it's the exact opposite trend as the size. Electronegativity actually increases as you go to the right. Why is that? Well, as you go to the right, there's a greater nuclear pull, and that's not only pulling the electrons of its own atom inwards, which is why it made it smaller, but actually if there's an atom right next to it, it's able to pull those electrons. So let's do an example. We're comparing potassium and bromine. So potassium has an electronegativity value, we assign it 0.8, and bromine has an electronegativity value of 2.8. Notice I'm not talking about krypton because again, krypton, very, very, very little, the lowest electronegativity, and we can think of essentially as 0 because it's a noble gas. So if there was another atom next to potassium, let's say another potassium atom, potassium can't pull an electron off of another potassium. So the electron's just going to be like, oh, cool, you're there, don't really care. But if there's a potassium atom next to bromine, bromine is a lot more electronegative, meaning it's able to pull electrons away. So bromine actually pulls electrons from other atoms because it's stronger. Because if you look at this nuclear pull, it's got a positive 30 right there and very little shielding. So that electron comes right off potassium because there's a stronger pull on bromine. And what about in the groups? Well, it's the opposite of what we learned before. So the increasing electronegativity goes up a group. So why do we see that? Because elements on the top have less energy levels. So if I compare over here, germanium, silicon, carbon, if I'm an atom outside of germanium, I barely can tell that germanium has a nucleus in the center because there's all these levels blocking it of electrons, and that's called electron shielding. So elements on the top have less energy levels, so it has less shielding of that nuclear pull, and an atom outside of carbon can feel carbon's nuclear pull a lot easier than if it was outside of germanium and feeling germanium's nuclear pull. The last trend we have to talk about is ionization energy. So ionization energy is the energy required to remove an electron from an atom. Now what you want to think about when you think about ionization energy is who wants to keep their electrons and who doesn't. So any atom that really wants to keep its electrons, they're holding on tight to those electrons. Whatever atom is pulling its electrons super tight close to the center, they're going to be really hard to remove electrons from. They're going to have the highest ionization energy. Think about like a kid with its like blanket that it loves, right? So that kid's holding on to his precious blanket. You're not going to be able to pull that blanket off of that kid, his comfort blanket or whatever. But if you give him like some Brussels sprouts, he might just like hand it out to you and say, here you go, I don't really want to hold on to this, right? How does that atom feel about the object? Is kind of like, how does the kid feel about his blanket versus Brussels sprouts? Okay, the blanket and Brussels sprouts are both electrons in this analogy. So here's just a little chart to go over ionization energies and what they are. And notice there's a bunch, I1, I2, I3. What is that? So the first ionization energy is the energy required to remove one electron. The second ionization energy is the energy to then remove a second electron. Now keep in mind, if you already pulled off one electron, that nuclear pull, it was dispersed amongst electrons. If you've removed an electron, all those electrons are being pulled even tighter to the atom, so it's even harder to remove a second electron. So that's why every single ionization energy increases as you go to the second ionization energy. And as you might imagine, the third ionization energy is the energy required to remove a third electron, and those get bigger too. So I3s are always the biggest, okay? So what do we see as the trends on the periodic table? So ionization energy matches the same trend as electronegativity, where it increases as you go to the right. Why is that? Well, same reason. It's got a stronger nuclear pull. This time, it's just talking about the nuclear pull on its own electrons. So since it has a strong nuclear pull on its own electrons, another atom can't just easily pull off an electron. You also want to think about who wants to keep electrons. Well, these noble gases are not going to get rid of any of their electrons because they're perfect. They have those perfectly full shell of electrons. But if we're talking about the alkali metals, like lithium, lithium is so annoyed with itself because if lithium loses one electron, it would be electrically like helium, which is like super cool because it's a noble gas. So lithium doesn't really want to keep an extra electron. It wants to get rid of one so it can be electrically stable like a noble gas. So if we compare straight across, like potassium wants to get rid of one electron so it'll be like a noble gas, versus bromine wants to gain an electron. It's certainly not going to let some other atom take an electron from it. So bromine, it would require more energy to take an electron from bromine than it was from potassium because potassium is trying to get rid of an electron anyway. So what about up and down the groups? Again, we're seeing the same trend that we saw in electronegativity. Ionization energies increase up the periodic table. And it's for the same reason. So the groups on the bottom are really big. So the groups on the bottom, those elements on the bottom, have greater nuclear shielding. So the electrons that are on the very, 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 very edge of cesium or francium, those really big atoms, they don't really feel the nuclear pull that much. So it doesn't take that much to remove an electron because the electrons are so far away from the nucleus that those outer electrons in cesium and francium, they're so far from the nucleus, another atom could just take away an electron, and those big, large atoms don't really notice an electron's even gone. So it's low ionization energy at the bottom because the outer electrons aren't held very tightly. High ionization energy at the top because the outer electrons are held closer than the larger atoms. All right, so that is the video on periodic trends. Good luck with this section, and I'll see you in the next video.